Hello. We will now talk about chapter 12, section 2, or at least the first part of it. I mean, most of it. I'm going to make two videos. And so this is going to be most and the main part of 12.2. And then I'll have another video that will do the last part of 12.2. And let me say before I forget, this year in regards to 12.2, we're not going to cover the uniform distribution during chapter 2, even though it's in your book. We're just going to go ahead and wait till later in the year to do that. So I just decided just to go ahead and wait till later to do that. So I don't think there's a point in doing it twice, really, and we're kind of limited for time. So we're not going to any problems dealing with the uniform distribution. We're not worrying about. But anyway. So 12.2 deals mainly with with density curves, and what we call the normal distribution is the main sort of thing we are going to work with. And first of all, definition: what is a density curve? It is just a curve that models a distribution. So in other words, it is just a representation of a list of numbers. It's just a graph of a list of numbers that we use to make, in essence, probability calculations. And so there's two qualities of what we call a density curve. First of all, it's always on or above the x-axis, and the area under it is always equal to 1. That allows us to make some easy calculations with it. And the main density curve, like I said, talked about, is going to be the normal curve. Now, any normal curve has this truth about it. For any normal model, approximately 68% of the values of the curve are within 1 standard deviation of the mean, 95% are within 2 standard deviations of the mean, and 99.7, or most all of the values, are within 3 standard deviations of the mean. That is what is known as the 68, 95, 99.7 rule. And when you look at a normal curve is a specific sort of bell-shaped symmetrical distribution. So if you go out 1 standard deviation to here and here, so here's the mean, there's sigma. And if you go up +1 standard deviation to there and -1 standard deviation to there, 68% of the curve, 68% of the values between there and there, 95% are going to be within 2 standard deviations. So about to there and to there. So -2 sigma and +2 sigma to there and there. 95% are between there and there. And then 99.7, or most all of the curve, is within 3 standard deviations. So 99.7 is within 3 standard deviations. Roughly, those are rough estimates. And so you have to know that the 68, 95, 99.7 rule. So let's do a couple of problems using the 68, 90, 95, 99.7 rule. So this says the times of the phone calls to the customer service department of a company following an approximately normal distribution. And by the way, so there's really no finite distribution that exactly follows the normal curve. Okay, so anytime you say the word, so nothing varies really exactly normally. So anytime you say the word normal, pretty much, you ought to say approximately normal, unless you're dealing with basically just a strictly theoretical problem, which we do sometimes. So we always say approximately normal distribution. And so in this case, we have a mean of 7 and a standard deviation of 1.5 minutes. Use the 68, 95, 99.7 rule to find. All right. So what we'll do is so first of all, we're going to, in essence, we're going to draw our curve. Okay. So let's draw our curve. So we'll draw our curve here. And so like this. And so for our normal model, the mean is 7. And so in other words, 7 is right in the middle there. When we go up 1 standard deviation, which is halfway down the hill here to this inflection point there, you go up 1 standard deviation, well, 1.5. So this would be 8.5. If we go up 2 standard deviations about to there, we add 1.5 again. And so that's going to be 10, and 3 standard deviations would be 11.5. Then if we go down 1 standard deviation to there, and so we subtract 1.5 from that, that'd be 5.5. Subtract 1.5 again, and so that would be 4, and subtract 1.5 again, so that'd be 2.5. So that's 1, 2, and 3 standard deviations. So in other words, with the 68, 95, 99.7 rule, 68% of the values are between there and there. Okay, 95%, let's see where I should write this, 95% are going to be between 4 and 10, and 99.7% are going to be between 2.5 and 11.5. And so what I want to do to do problems now, by the way, doing what we're fixing to do here, when I do the other examples, you're going to say, well, what's the point of using this rule? Because I use my calculator to find it, but you still need to understand this rule. All right, so I'm going to find, in essence, the percent that is in each of these sections in order to be able to answer problems like that. So like if 68% is between 5.5 and 8.5, so that means 34% is there and 34% is there. And so then what percent is like in this section and in this section? Well, if you said 95% minus 68%, so that is going to be, so that's going to be like 27%. And so in dividing it by 2, that would mean there's 13.5% in each of those, 13.5%. Then if you went out 3 standard deviations, 99.7, and if you subtracted, so to there, and if you subtracted 95%, so that is going to be like 4.7%, which means there is going to be like 2.35% there and 2.35% there. And then how much is on the outside beyond 3 standard deviations from the mean? Well, the whole curve is 100%, and that's 99.7. So it's 0.3% on the outside, and there's 2 parts of it. So that ends up being 0.15% on each tail, 0.15%. And so what percent are more than 8.5? More than 8.5? Well, you can just, in essence, add those 3 numbers up. So greater than 8.5 is going to be, when you add these numbers up, is going to be equal to 16%. So that is using the 68, 95, 99.7 rule. All right. So what percent of the peaches weigh between 4 and 11.5? Well, between 4 and 11.5, you would add these numbers up: 13.5, 34, 34, 13.5, and 2.35. And those numbers add up to 97.35%. Okay. Now, and so that's something that you need to understand. Now we're going to talk about sort of a shortcut, the way we're really going to do normal problems. All right. To show your work in a normal calculation, there's 3 things you got to be able to do, and you'll be asked to do. All right. And number one is to draw the curve with shading whenever you're given a normal problem. Okay, it's not a multiple choice problem, so you have to show your work. So always draw the curve with the proper shading, and I'll demonstrate this. Number 2 is find the z-score. Find the z-score of the problem. Okay, and I'll demonstrate that. And then number 3 is find the answer. Okay, which you in essence can use your calculator. You can use a table, which I'm going to show you, or you can use your calculator. But those are the 3 ways, 3 things you need to be able to do in order to show your work. So let's do that here. So here's the main problem of the section. All right. The scores on a test vary approximately normally with a mean of 81.4, standard deviation of 3.6. If you randomly select one of these scores, find the probability to be less than 76. So to do this normal problem, I'm going to draw the curve like that, draw the curve. And so label it as normal. That's important. We have other curves that are going to look like this, so make sure to label it properly normal. Now, the mean is right in the middle, so the mean is 81.4. And then standard deviation of 3.6. Well, if you go up 1 standard deviation, so that takes me up to 85. And really, you just need to mark 1 standard deviation would be fine. And if you go down 1 standard deviation, so that would take you to 77.8. Okay. So the question is, if you randomly select one of these scores. Every point under this curve is a score. What's the probability it's going to be less than 76? Well, 76 is somewhere over here. And so less than 76 is that. And so our shaded region is to the left. So that's what it means to draw the curve and to show the shaded region. Okay. Now, to find the z-score. So we'll find the z-score. Now, you say, why are we finding the z-score? Well, it allows us to use our table to, in essence, find the answer. Now, we could use our calculator right here to find the answer, but you've got to be able to use the, you've got to be able to find the z-score and find the table. So use the table. So our z-score is going to be equal to 76 minus the mean, as we did in section 1 of chapter 2, over 3.6. And so let's see what that is. And so 76 minus 81.4 is equal to, divided by 3.6. And so that is equal to negative 1.5. That is our z-score. All right. So now the last thing is to find this area, to find the answer. And so to find this answer, what we're going to do, since we have the z-score, is we're going to go to our z-score table. So this is the first of our tables that does standard normal calculations. Standard normals means basically their z-scores. And so this is table A. You'll notice the nice normal curve here, and you'll notice this shading that's to the left of the z-score, right? So that's what this table is telling you. It is telling you the area to the left of your z-score. And so we'll find our z-score. So here on the left side, you notice it says Z, and then down the left column here is the first 2 digits of your z-score. And over the top row is the hundreds digits, which we don't have one here. It's just negative 1.50. And so we will go to negative 1.5. And by the way, if it was a positive z-score, you go to the next page. The next page has your positive z-scores, but it's still the area to the left of your z-score. So this is what we want here. So we want the area to the left of negative 1.5. So we go to negative 1.5 right there, and our hundredths place in our z-score is 0. So it's 0.0668, and that is our answer. So the probability that we are going to get that our x is going to be less than 76 is the same as the probability of our z-score being less than negative 1.5, and that is equal to 0.0668. That would be, in essence, fully showing your work. Okay. All right. Now, let me show you, in essence, how you're really going to do these problems with your calculator. So with the calculator, what you'll do to do this problem is this. We're going to use what is known as normal CDF. All right. So normal CDF is above the vars button. There's the distribution button. You're just going to go second distribution, which is with second vars, which is distribution, and go to normal CDF, the second one down. That's the main command. These are our main 2 commands of this chapter. So we go normal CDF and we hit enter. Now, so we enter in our shaded region. So our shaded region is, it's from negative infinity to 76. So my lower bound is negative infinity, which is that. Or you could just enter in like, you know, negative. And by the way, the negative button is below the 3. Hit the negative button, that, not the minus button, which is that, or you'll get an error. So negative. So if we just hit like negative, a big number, and then the upper value of my shaded region is 76. Then mu, that's my mean. My mean in this problem is 81.4. And then my standard deviation is 3.6. So I get 3.6 like that. Now, some calculators will immediately take you to this screen. Okay, immediately take you to this screen. Okay, and what you would do, and so, so as a matter of fact, I'm going to just delete this out. Let's just pretend when you call up your calculator command, your screen looks like that. Okay, what you're going to enter in, the order, you have to enter in 4 numbers. The left bound, which is negative infinity, so you go negative 999, and then to 76 is my upper bound. So I hit comma. Comma is above the 7 button. It's above the 7 button, so you go comma, and then 76. Okay, and then comma again, the mean 81.4, and then comma the standard deviation of 3.6, and then you can just hit enter, and there's the answer. And so that's how you do it. And that's the main command of this chapter. Now, to show your work, okay, like I said, you know, so there's 2 ways of showing your work, really. showing the curve, the z-score, and the answer, just like in essence I did here. The quickest way to do it, though, is to write normal CDF and then write your numbers properly labeled. So negative infinity is my LB for lower bound. 76 is my UB for upper bound. All right, 81.4 is my mu. And then my sigma is going to be 3.6, like that. And that is equal to 0.0668 approximately. Okay, so but if you do not label them like that, you get partially correct. But if you just wrote that, you would get full credit. Okay, unless you were told to show the curve and the z-score. All right, so I encourage you to certainly at least draw the curve so you can orient yourself. But yes, if you just wrote what I just circled here, you would get full credit for showing your work. Okay, but like I said, you have to be able to draw the curve and define the z-score because you could be asked to do that. All right, what's the probability? Number 4, what's the probability that you'll get a value greater than 83? Well, let's mark that. So 83 is right up here somewhere. So there's 83, and we're shading above it. So we'll do normal CDF. Normal CDF from 83 to infinity. All right, our mean is 81.4, and our standard deviation is 3.6. We have to label these, do it every time. LB for lower bound, UB for upper bound, mu, and then sigma, and let's see what we get. And so I'll go second VARS, which is distribution, normal CDF. And so now we are going from 83 to infinity. So I'll just go 83, comma, or not comma, sorry. You just hit 83 and then arrow down to infinity. So you get like 9 million. That'll work. And then same mean, same standard deviation, paste. Some calculators will immediately take you to this screen right there. So you just enter those numbers like that. Okay, hit enter. And there's our answer, 0.32. So that would be 0.32836. Thus, the answer to number 4. Number 5, what about in between 75 and 84? Well, 75 is like right here, and 84 is like right here. So what about in between those two numbers? So what we'll do is we shall say normal CDF from 75 to 84. 75 is my lower bound. 84 is my upper bound. My mean is, once again, 81.4. That's my mu. My sigma is 3.6 sigma. If you don't like writing the Greek letters, you could just write the words mean and standard deviation, by the way. So let's see what we get there. So we'd say second distribution normal CDF. And so we're going from 75 to 84, 75 to 84. Our mean is 81.4. And our standard deviation is 3.6, which is the same. And so that would be equal to 0.7272. There we go. And thus, that's the answer to number 5. All right. The other, so normal CDF, one of your main types of problems. And once again, going back, many people find, you know, what I did here with the 68, 95, 90.9.7 rule is confusing. And you may say to yourself, why don't we just do normal CDF to find this and normal CDF, you know, to find that? And the answer is yes, you can. Okay. But I needed to expose you to this rule because you could be asked about this rule. Okay. So yes, you can use normal CDF to solve this problem. All right. Now, here's the next type of problem. What's the 70th percentile of the scores? Now, what that means is this. Here's our normal curve. Of course, we have a mean of 81.4. You go up 1 standard deviation to 85. You go down standard deviation to 77.8. There it is. Now, this one gives us the percentile, which is it. So it's asking what value is greater than or equal to 70% of values. So 70%. So we have a value somewhere over here. We don't know what it is. I'll just call it X. And it is larger than 70% of values. That's the 70th percentile. So I need this X value there. Now, with normal CDF, what was happening is they were giving us like the X values and asking us to find the areas, like less than 76. It gives us the X value to find the area. That's a normal CDF problem. So this is an inverse norm problem. Inverse norm is when they give you the area or the percentile or the percent less than that, and they ask you to find the x. And so the command we're going to use to find the x is inverse norm. And it's easy to kind of get inverse norm and normal CDF mixed up. But if you thought to do normal CDF here, what would you enter for your upper and lower bound? You wouldn't know what your upper bound was. So it wouldn't work. So we do inverse norm in our area. We put it in decimal form, 0.7. And we label this as our left area. And then you put the mean and standard deviation, 81.4 and 3.6. So this would be my mu. This would be my sigma. And so here we go. And so inverse norm is right below normal CDF. So I'm going to go second vars, which is distribution, and go inverse norm right there. Those are the two big commands of this chapter that you got to be able to do. Okay, inverse norm. And on my left area is 0.7. Notice, by the way, your calculator automatically put a mean of 0, standard deviation of 1. That's going to be important in a minute. So our mu is 81.4, and our standard deviation is 3.6. And then I always use left area. Some calculators don't give you this option of left area, center area, or right area. And that's a convenient command. I tend to always use left area because some calculators don't have that command. So, and then we hit paste. Now, many calculators are just going to give you this command. It's just going to say inverse norm. And if it does that, just enter those three numbers separated by comma, the left area, comma, the mean, comma, the standard deviation, and then it won't say left there. But so I hit enter and that's it. So that's the answer, 83.288. So this is about 83.288. And this is test score, so it doesn't have a unit. So, and that seems to be reasonable as far as an answer. And that's it. So that's an inverse norm problem where it gives you the area or it gives you the percent and it asks you to find the X value. Okay. So what percent is less than 80% of scores? Let's think about that. It's less than 80% of scores. Well, I mean at 81.4. So it means 80% is above it. 80% is above it. Now, once again, I tend to always use left area. So if 80% is above it, and so I got to find this X value. Okay, so this is an inverse norm problem. Well, if 80% above it, 20% is below it. Okay, and so we will say inverse norm of 0.2. That is my left area. Now, technically, you'd use a right area. Once again, I always use left area because some people's calculators don't have a right area, but 0.2, our mean of 81.4. And our standard deviation at 3.6. Always label these with mu and sigma. If you forgot to label these things, then you would just get partially correct. And so to show your work on this, all you have to write is inverse norm with the properly labeled parameters here, the properly labeled numbers. I encourage you to draw the curve, just a rough sketch of the curve so you can orient yourself and make sure that your answer makes sense, by the way. So let's do this. So we shall do second vars, which is distribution, inverse norm, 0.2, mean of that, left area, boom. That's it. So that's our answer. So our answer is 78.3702. Let's look at that and see if that makes sense. That seems reasonable right there. So, and by the way, if you could do right with my calculator here, you could do right area. If you do of 0.8, if you go to 0.8 and go right area, you would end up the same answer. So anyway, okay, now, so that's really the main part of the section. There's also another concept here, and that's what is known as the standard normal curve. All right, the standard normal curve is in essence a curve of z-scores. It is a normal curve. It is a normal curve with the mean mu, with the mean mu equal to 0 and the standard deviation equal to 1. So this would be symbolized like this notation means a normal curve, mean of 0, standard deviation of 1. It is in essence a curve of z-scores. It's a curve of standardized values. You know, the z-score is the number of standard deviations you are from the mean. They're standardized values. And if you were to standardize every value in a normal curve like this one, in other words, take every point and subtract the mean and divide by the standard deviation and get a z-score, it would create the standard normal curve with a mean of 0 and a standard deviation of 1. And we're going to use this in essence to find z-scores and to and to solve various problems. So that's what is the standard normal curve. It is a curve of z-scores of standardized values. What is it? And by the way, another bit of terminology, a decile. A decile is just, and it's, you know, think metric system with decimeter or whatever. It's just, it divides a distribution up into tenths. So the second decile is in essence the 20th percentile. So the 20th percentile, and that would be the 80th percentile of the standard normal curve. Standard normal curve, that means mean of 0, standard deviation of 1. So how do you find the 20th percentile? That's with inverse norm. So we'll say inverse norm of 0.2. That is our, please label left area and mu and sigma, so you'll get full credit. Thank you. Mean of 0, standard deviation of 1. That is my mu and my sigma, like that. And so the decile just means that it's in tenths. And so we will say inverse norm of 0.2, mean of 0, standard deviation of 1. And your calculator resets to that after a while, by the way. So we go like that. And so that would be negative 0.8416, right, like that. So that's the 20th percentile. And the 80th percentile, guess what it's going to be? Now, you know this thing's going to be perfectly symmetrical, by the way. Mean of 0, standard deviation of 1. So this thing's like down here. Well, if you go the 80th percentile, it's going to be up here. So we'll do inverse norm of 0.8, mean of 0, standard deviation of 1. Now let's see what that is. I'll just re-enter that command and just change this to 0.8. It's going to be the same thing, but positive. So it's going to be 0.8416, like that. And so, so there you go. So that's how you find deciles. So there we go. All right. So now here's a couple of, I've got, you know, 3 of, you know, problems here that are kind of viewed as sort of tougher sorts of problems. But let's see if we can work these out. These sorts of things have been on the exam, and actually not a ton of people got these right. But let's see if we can figure these out together. So we have a drink machine that dispenses amounts of Mountain Dew in slightly varying amounts. The amounts vary approximately normally with a standard deviation of 0.18 ounces. Okay, it doesn't tell us the mean, by the way. So the mean can be preset by a worker. What should the worker set the mean to if he wants a 16-ounce cup to be overfilled only 1% of the time? So we have, in essence, this normal curve that represents each point in this here is the amount that the drink machine is dispensing. We don't know what the mean is, so this is mu. We do know that the standard deviation is 0.18. We also know that we only want a 16-ounce cup to overfill over 1% of the time. So let's just pretend, so this 16 is somewhere up here. The reason I put it up there, it says that this curve is going over 16 only 1% of the time. So only 1% of this curve is over 16. So this right here is 1%. All right. In general, when you're working with normal curves, when you don't know mu, or if you don't know sigma, we're going to use a formula that has mu and sigma in it. Can you think of a formula that has mu and sigma in it? That's right, the z-score formula. The z-score formula is x minus mu over sigma, okay? And so now, so we know what x is. Our x is 16, okay? We know what sigma is. We're trying to figure out what the mean is. What is the z-score? Well, we can find this z-score right here using inverse norm with the standard normal curve. And so we would realize if 1% is to the right of this value, that means 99% has to be the left. So this thing is this point here, it is at the 99th percentile. So let's use inverse norm to find the z-score for that. Inverse norm, so we'll go 0.99, that is our left area. So that is our left area. Mean of 0, standard deviation of 1, that's our mu and sigma. When you use inverse norm of the standard normal curve, it tells you the z-score. So let's do that very thing. And so we will say second distribution, inverse norm of 0.99, mean of 0, standard deviation of 1. We're working with a left area. We do that, and there's the z-score, 2.326 about. So that is our z-score. So we'll enter that into our formula. 2.3263 is equal to the x value is 16 minus mu over our sigma of 0.18. And so I'll just use my algebra skills here to solve for mu. I'll multiply this number. So I'll say 0.18 times both sides. So I'll get times 0.18. And so that would leave me with 0.4187 is equal to 16 minus mu. And then just subtract 16 from both sides. Minus mu is equal to this minus 16. And so this would be negative 15.58. And so therefore my mu is equal to 15.581. And this is ounces. And that's how you do that problem right there. So the key thing, the key little trick was realizing I can find the z-score on any normal curve by using inverse norm of mean of 0, standard deviation of 1. And then, so that's how you do that. All right, so then we have this is a similar sort of thing. In number 9, the mean is set at 15.8. All right, however, the standard deviation is no longer 0.18. What would the standard deviation need to be if you want the dispenser to overfill only 3% of the time? So now it's a similar sort of thing. We know that the mean is set at 15.8. So 16 is somewhere up here. We know that 3% of the curve is above 16. So here's 16. We know that this is 3%. Well, that means in essence, this is the 97th percentile. If you say 100% minus that. So 97% is over here. Okay. So we need, once again, whenever you don't know mu or sigma, you're going to use the formula for z-score. So we'll use the formula for z-score. Our z-score is equal to x minus mu over sigma. And so let's find the z-score for 97%. And so we will say inverse norm, 0.97, mean of 0, standard deviation of 1. That is my left area. That is my mu. That is my sigma. And so here we go. And so we shall go second distribution, inverse norm, 0.97, mean of 0, standard deviation of 1. Calculate my z-score is 1.88. So I have 1.88079 is equal to my x value is 16 minus my mean is 15.8 over sigma. And that's what we're trying to find. We don't know the standard deviation here. So we'll just solve this using our algebra skills. 1.88079 is equal to that minus that would be 0.2 over sigma. Multiply both sides by sigma. And this ends up being 0.2 divided by that. And so I'll just say 0.2 divided by that. And so that would be 0.10634, let's say. And there we go. So certainly those are a couple of the harder problems that you would have. And then lastly, let's see if we can find outliers. All right, so it says the ACT scores of students in a large school district follow an approximately normal distribution, mean of 18.5, standard deviation of 3.9. What are the outliers? Well, remember our formula for outliers. So what are the outliers, question mark? Our formula outliers, Q1 minus 1.5 times the IQR. Or in less than that. Remember to put the less than, or greater than Q3 plus 1.5 times the IQR. You have to memorize those formulas. Well, so let's find the IQR. So you remember the IQR is equal to Q3 minus Q1. Well, what is Q3 and Q1? It's the 75th percentile and the 25th percentile. Well, how can we find percentiles in a normal curve? And that's with inverse norm. So Q3 is the 75th percentile. The way you can find that in a normal curve is inverse norm of 0.75. In this case, mean of 18.5, standard deviation of 3.9. Please always label these so you'll get full credit. Left area, mu and sigma. Okay, and then we'll find that, and then minus Q1 is inverse norm of 0.25, same mean, same standard deviation. So let's see what we get. And so we'll do inverse norm, second vars, which is distribution, inverse norm of 0.75, And our mean is now 18.5. So 18.5, standard deviation of 3.9, left area like that. So this is 21.13. So Q3 is 21.1305 minus, and so I'm going to label that as Q3. Okay, so Q1, I'll just go up and call that and just change this to 0.25. That'll be the first quartile or the lower quartile, 15.8695. So 15.8695. So let's subtract these two numbers and get our IQR. So our IQR is going to be equal to 21.13051 minus 15.869. And so that's 5.261. So that minus that would be 5.261. Now I can enter these in the formula. So for my lower bound, it would be anything less than our Q1, which would be 15.8695 minus 1.5 times 5.261. And when you do that operation, you would get, that would end up being less than 7.97796. So anything less than that's an outlier. And then this part of it, anything greater than my Q3 is 21.1305 plus 1.5 times 5.261 like that. And when you do that arithmetic there, it'd be anything greater than 29.022. So there you go. That's it. And that's the main part of 2.2. We also have assessing normality, which is going to be on the next video. But anyway, thanks for watching, and then please send me any questions you have, and I hope you have a great day.